Hi folks, this is our first video on reactivity. I'm going to be talking about thermodynamics, kinetics, and reaction coordinate diagrams. I'll start by talking about a thermodynamic property known as enthalpy. Enthalpy is denoted with a capital H, and delta H is the change in enthalpy for a reaction. Enthalpy is a measure of how much heat is released or absorbed in a process. For a chemical reaction, you're going to look at two things related to enthalpy. One is how much energy is required to break the bonds on the reactant side of the chemical reaction. And two is how much energy is released when you form bonds that are present on the product side of the reaction that weren't there in the original starting materials. As a measure of these energies required to break bonds or form bonds, we're going to use bond dissociation energies. These are a measure of how much energy is required to homolytically break a bond. Let's imagine we had a bond between X and Y atoms. A homolytic bond cleavage is imagining just simply chopping this bond in half. This bond contains 2 electrons, and in a homolytic bond cleavage, one of those electrons goes to X and the other electron goes to Y. The total change in enthalpy for a reaction, called delta H for that reaction, is known as the heat of reaction. A reaction that requires heat from the surroundings is known as an endothermic reaction. In this case, the heat of reaction, delta H, would be positive. An exothermic reaction is one where the reaction gives off excess heat to its surroundings. For an exothermic reaction, the heat of reaction delta H will be negative. Let's consider a general reaction of a starting material A going on to form a product B. Here I'm showing 2 diagrams where I'm plotting enthalpy on the y-axis and the course of our reaction going from A to B over a barrier on the x-axis, known as the reaction coordinate. I have 2 different scenarios here based on the relative enthalpies of A and B. In the left graph, notice that B is lower in enthalpy than A. The heat of reaction would be negative, and we would call this reaction exothermic. In the other graph, product B is higher in energy than reactant A. Delta H here would be positive, and we would call this reaction endothermic. We can predict delta H for a reaction using bond dissociation energies. Here's an example reaction where I'm starting out with an alkane and treating it with Cl2. And the products are an alkyl chloride and HCl. The first thing you want to do is identify the bonds being broken and formed. The bonds being broken are the ones that appear on the reactant side but not the product side. This is a carbon-hydrogen bond of the central carbon and the chlorine-chlorine bond. The bonds I'm forming are a carbon-chlorine bond and a hydrogen-chlorine bond. These are bonds that are there in the products that weren't there in the starting materials. Next, you want to look up bond dissociation energies for these bonds that are being broken or formed. Here I've provided you those bond dissociation energies in units of kilojoules per mole. Then to predict delta H for the reaction, you want to take the sum of the bond dissociation energies for your bonds broken and subtract from that the sum of the bond dissociation energies for the bonds formed. In this case, the bond dissociation energies for the bonds broken are 381 and 243, and those for the bonds formed are 331 and 431. Overall, I calculate delta H for this reaction shown above as negative 138 kilojoules per mole. Because this value is negative, I would call this an exothermic reaction. Now I want to talk about a second thermodynamic metric, entropy. This is a measure of degrees of freedom, or freedom of motion, of a system. In our case, a chemical reaction. The change in entropy for a reaction, delta S, will be positive when the reaction increases the number of molecules present, or if during the reaction you have an increase in the amount of free rotation, meaning bonds can rotate more freely in the product compared to the reactants, or delta S will be positive if your reaction forms a gas from solids or liquids. As an example, let's consider a reaction where we have a bond between A and B in the reactants, and we have separate molecules A and B on the product side. I have one molecule starting out, and I'm forming two molecules in the products. Because I'm increasing the number of molecules present, I would expect that delta S would be positive for this reaction. Here's a more concrete example of a reaction where delta S is positive because the number of molecules is increasing. Here I'm starting out with an alcohol, and in the presence of a catalyst, I'm forming an alkene and water. This is a reaction that you'll see later in this semester. Another common scenario for a change in entropy is if you have a ring starting out, and then that ring breaks during the chemical reaction. We would call the starting material containing the ring cyclic, and the product that has lost that ring acyclic. Acyclic molecules have more rotations about their bonds that are possible compared to cyclic ones. So for this reaction, we would predict delta S would be positive. An example of this type of reaction is shown below. I have a cyclic ester starting material, and I'm treating it with H3O+, an acid, to form a molecule that is acyclic and contains a carboxylic acid and an alcohol. This is a reaction that we would be encountering in the spring semester of organic chemistry. Our final thermodynamic parameter that I'll talk about is Gibbs free energy, known as delta G. Gibbs free energy is related to enthalpy and entropy by the equation delta G equals delta H minus T delta S. We'll call a reaction exergonic if the Gibbs free energy is negative for that reaction. When delta G is negative, this is a spontaneous reaction and will be favorable. If the Gibbs free energy for a reaction is positive, we'll call it an endergonic reaction. And endergonic reactions are not spontaneous, and they are unfavorable. Let's consider a general reaction again of A going to form B. We have two different scenarios. You could have A with a higher Gibbs free energy than B, or B with a higher Gibbs free energy than A. Notice that in the left graph, the Gibbs free energy of B is lower in energy than of A. In this case, the delta G for this reaction would be negative, and we would call it an exergonic reaction. In the other graph, B is higher in energy than A. For this reaction, delta G would be positive instead. And because of this, we would call this an endergonic reaction. Related to Gibbs free energy is the concept of equilibrium. Here let's consider we have starting materials A and B going to form C and D as products. We can define an equilibrium constant, KEQ, as being equal to the concentrations of the products divided by the concentrations of the reactants. If KEQ is greater than 1, that means that your numerator is larger than your denominator, meaning the concentrations of your products C and D is higher than your concentrations of reactants A and B. This indicates that the products are favored in this case. If instead the equilibrium constant is less than 1, that means that your denominator is larger than the numerator, meaning your concentrations of starting materials A and B are larger than those of your products C and D, and we would call this reactants being favored. Delta G is related to the equilibrium constant by the equation delta G equals negative RT natural log of the equilibrium constant KEQ. I want to show you some examples of relating Gibbs free energies in kilojoules per mole to equilibrium constants and the amount of products you have. If delta G is negative 11 kilojoules per mole, you could calculate the equilibrium constant would be 1,000, and this would correspond to having 99% products at equilibrium. If delta G is less negative, or negative 6, KEQ is smaller, but still greater than 1, and this corresponds to 90% products present. If delta G is exactly 0, you'll have KEQ equal to 1, and this will mean you have equal amounts of starting material and products present, or 50% products. And if you make delta G positive, this would be an unfavorable reaction. Your equilibrium constant would be less than 1, meaning your reactants are favored, and you would have only 10% products present. So notice the more negative delta G is, the more favorable the reaction is, corresponding to a larger KEQ. Now I want to talk about the realm of kinetics, which has to do with rates of reactions. In the most general form, the rate of a reaction will depend on a little k value and concentrations of reactants in some form. Lowercase k is the rate constant, and your concentration term involves the starting materials. The effect of these concentrations on the rate cannot be predicted and needs to be determined experimentally. Let's say you had a reaction involving starting materials A and B. You would start by thinking about a general rate law, where you have a rate constant, the concentration of starting material A to some power x, and the concentration of starting material B to power y. Let's say you experimentally determined that the rate was equal to the rate constant times the concentration of A to the first power. We would say that this reaction is first order in A and 0 order in B. Alternatively, let's say you determined your rate law to be equal to the rate constant times the concentration of A times the concentration of B. We would say this reaction is first order in A, because it's A to the first power. We'd also say it's first order in B because it's B to the first power. And because it's first order in A and first order in B, we would call this reaction second order overall. The rate of a reaction will be affected by a few factors. One of these is the energy barrier, known as the energy of activation, EA. This is the amount of energy it takes to go from starting materials to products. Let's consider two different energy diagrams. In both cases, product B is lower in energy than A, and what's changing is the barrier height, or the blue curve going between A and B. I measure the barrier from the energy of starting material A to the top of the barrier. Compared to the other graph, this is a small energy of activation. And we would expect this to be a fast reaction because it has a low barrier. In the other graph, here I'm measuring the energy of the barrier from the energy of starting material A to the top of the peak. Compared to the other graph, this is a larger energy of activation. And the larger this barrier, the slower the reaction is going to be. A separate factor that will affect the rate of the reaction is temperature. As you increase the temperature, the rate is going to increase. Temperature is giving your molecules more energy so that they can get over the barrier more readily. Another factor that can affect the rate of a reaction is whether or not you have a catalyst present. Catalysts will speed up a reaction without being consumed. And they do this by providing a lower activation energy pathway. Let's imagine that this reaction all by itself has a high barrier. If you add a catalyst that's appropriate for this reaction, it'll provide a lower energy barrier pathway between the two. Notice that the barrier height was high without the catalyst present, and the largest barrier that you encounter through the catalyzed pathway is much lower. This smaller barrier means that the reaction is going to proceed faster. The catalyst affects the barrier heights, but be careful. The catalyst doesn't change the energies of the reactant or the product. A and B are at the same energies as before. And the values of Gibbs free energy and the equilibrium constant depend on the energies of A and B, which will not be affected by the presence of the catalyst. I want to highlight the difference between when we're talking about kinetics compared to when we're talking about thermodynamics. In the case of kinetics, you're thinking about the rate of the reaction. This has to do with the difference in energy between your starting material and the highest energy barrier it encounters. This energy is the activation energy. And the higher the barrier, the slower the reaction. Notice that the energy of product B does not matter at all for kinetics. In contrast, thermodynamics is looking at equilibrium. I'm considering the energy of starting material A relative to the energy of product B, and I measure this as the free energy for the reaction, delta G. This is also related to the equilibrium constant KEQ. Notice that thermodynamics isn't concerned at all with the energy of the barrier. That's solely in the realm of kinetics. For reaction coordinate diagrams, it's important to know the different locations along them and what they symbolize. Let's consider a more complicated reaction coordinate diagram than we've seen before. I start out with A, go to B, carry on to C, and then eventually form a product D. I'll call intermediates the product of one reaction step that becomes a reactant for the following step. These are going to look like local minima on the energy diagram. The reaction coordinate diagram shown above has two intermediates, B and C. In contrast, on the diagram, transition states will be high energy states. These will be local maxima along the energy diagram. These three high points in energy between A, B, and C are my transition states. Counting the number of transition states tells you how many steps your reaction has. One step to go from A to B, a second step to go from B to C, and a third step going from C to D. These transition states, or local maxima along the pathway, are fleeting. They only exist for a fraction of a second, and they cannot be isolated, or often even observed. At the transition state, bonds are being broken and formed. Let's consider an acid-base reaction between the acid HCl and water acting as a base. I'll draw in my two curved arrows from the water lone pair to the proton, then from the middle of the HCl bond to chlorine. And this forms my H3O+ and chloride anion. The products here are favored because HCl is such a strong acid compared to H3O+. On a reaction coordinate diagram, I would show the products, H3O+ and chloride, as lower in energy than the reactants, because the product side is favored. Because this reaction occurs in a single step, I have a single barrier between starting material and products. I want to focus in on the transition state, because at the transition state, I have my water molecule coming in and forming its new bond to the hydrogen, and the hydrogen-chlorine bond breaking at the same time. I use a dotted line to represent the bond that's forming, in this case, the OH bond. And I also use a dotted line to represent the bond that's breaking, the HCl bond. Transition states are typically drawn in brackets, and they're given this double dagger sign. This denotes that it's a transition state. What's known as the Hammond postulate talks about the structure of the transition state. And the Hammond postulate states that the transition state will most closely resemble the reactant or product that it's closest in energy to. Let's consider a single-step reaction for A going to B. In one scenario, I have an exergonic reaction where B is lower in energy than A. This would be a favorable reaction. And in the other case, I have an endergonic reaction where starting material A is lower in energy than B. This is not a favorable reaction. What you want to look for the Hammond postulate is which is the transition state closer to, the reactant or the product. For the exergonic reaction, notice that the transition state is closer in energy to reactant A than it is in energy to product B. By the Hammond postulate, because the transition state is closer in energy to the reactants, it will resemble the reactants more. For the endergonic reaction, notice that the transition state is closer in energy to the products than it is to the reactants. In this case, again by the Hammond postulate, because the transition state is closer in energy to the product, the transition state more resembles the product. All right, so in summary, today's video talked about thermodynamics with properties like enthalpy, entropy, Gibbs free energy, and equilibrium. And I also talked about kinetics, rates of reaction, having to do with barrier heights, temperature, or the presence of a catalyst. I've also introduced reaction coordinate diagrams, showed you what intermediates versus transition states look like in these. That's it for this video. I will see you in class.